Good afternoon. So, we will continue with the definitions for fire. Let us first take the ignition. So, fire is basically initiated by an ignition. As I told yesterday in the last class, if you have a source which is flammable and accidentally you cause a ignition there, like for example, you throw some ignited cigarette or any other matchstick etc. Into a dustbin where some papers are present. So, accidentally ignition is caused. So, it will initiate a small fire. This fire, based upon its strength and the availability of the other commodities around the source of the ignition, you will see that the fire will spread and it will grow in size and so on. So, ignition is the first process which will initiate a fire. So, for a material to get ignited, its temperature should reach a value called ignition temperature. So, the ignition temperature is the minimum temperature which will cause ignition. So, for example, in the liquid fuels, we have shown that there is a minimum temperature called flash point which will produce some vapors that will mix with air, and if upon production of an ignition source, a flash or instantaneous flame will be produced. So, it is something like that. Now, for the material to get heated up from the room temperature or the initial temperature to the ignition temperature, you need what is called a critical heat flux. So, that is also important. So, for example, if the heat flux is incident to the surface is the heat flux basically. If the rate at which heat is coming in, but the rate at which heat is lost, okay, this should be compared. So, if the rate at which heat is coming in is comparable or lesser than the rate at which heat is lost, then the material will not be heated up at all. So, for the material to be heated up, the critical heat flux is required. Now, there are several properties of the material which will dictate the time taken for ignition. So, we have seen a property combining density, thermal conductivity and specific heat, which is called thermal inertia, rho Kc, product of this. Then the heat of gasification and pyrolysis. In the case of solid fuels, we say that it is a heat of gasification, that is the heat required or supplied to gasify or release the volatiles present in the solid, or it may be latent of vaporization in the case of liquid, where the liquid has to be supplied with that heat in order to make the liquid vaporize from liquid to vapor. Now, ignition temperature, another thing what we are told, this may be a saturation temperature at a given pressure for the liquids, or the ignition temperature will be close to pyrolysis temperature in case of solids and so on. Okay. Now, more than this, the product yield during pyrolysis, when the volatiles come out of solid, how much products come out, that is also going to dictate the ignition. That is time taken for ignition. So, these parameters together is called thermal response parameter, TRP. And also we saw the ignition can be either a piloted ignition or an auto ignition. If you use say external source like a candle or a spark etc., then the ignition is piloted ignition. In this case, we need to have some volume of flammable mixture to which the ignition is provided, external ignition source is provided. Thus, that should be minimum volume. The minimum volume or critical volume is determined by if the mixture in the given volume burns, the heat release should overcome the heat loss from that particular domain. So, there is a minimum or critical volume of reactants which are required. Similarly, the ignition energy should be there, proper ignition energy should be provided. If the energy of ignition is very low, say for example spark has some strength, correct. If the strength of the spark is very low, then again it cannot cause the ignition. Okay, so these are the two criteria to be met for pilot ignition: minimum volume or critical volume of the mixture, reactant mixture to be present, and the minimum ignition energy for the source. Now, Auto ignition on the other hand will contain a reactant mixture which is flammable in nature, and its temperature also is higher, quite higher. That is, its temperature is more than what is called auto ignition temperature. In that case, there is no need for providing the external ignition source, because the reactant mixture at the flammable condition is present at a required temperature for it to react straight away. So, there is no need to provide additional energy like in piloted ignition. So, for example, if the flame is formed over the surface of a solid fuel or a liquid fuel, then the gases which are coming out, they can go to this high temperature immediately because of the flame heat feedback. So, there continuous auto ignition occurs to sustain the flame. Auto ignition also occurs in several other cases which we will see later. So, now auto ignition are of different types basically. The first one is, see, for example, let us take a coal mine where lot of coal dust will be present. The coal dust will be settled over some surfaces like say motor casings or switch boxes, etc., which can be hotter sometimes. Okay, so if a layer of combustible dust like coal or any organic dust like powders, powder manufacturing industries have powders. So, when they manufacture that, the powder will actually evolve out and they may settle as layers in some surfaces which may be hotter due to some process. So, if a layer of combustible dust settle over a hot surface, then what happens is, based upon the surface temperature, the temperature of the dust layer will increase beyond the value of the surface temperature itself. See, for example, wall temperature is say 300 degrees centigrade. The dust layer, say a 1 inch dust layer is deposited over this surface of 300 degrees centigrade. Then, due to auto ignition, the layer's temperature can increase beyond 300 degrees centigrade because of what is called spontaneous ignition. The spontaneous ignition of dust layers can cause massive ignition sources and lead to dust explosion. Okay, so that also we will see later. So, that auto ignition can cause a spontaneous ignition in dust layers, not only in a reactant mixture which is a gaseous form. Now, let us take reactant mixtures present in confined space. For example, in a volume there is a reactant mixture. It may be a gas, fuel and oxidizer mixed in flammable proportion. Now, if the temperature of this is higher enough, then auto ignition can occur, and such situation will lead to explosion. This need not happen only with gaseous fuels, it can also happen with say dust, some dust particles. Dust particles are nothing but, when I say dust, it is say less than some 100 microns. So, such small particles is termed as dust. If dust is actually forms a cloud with the air, mixed with air and forms a cloud, and its temperature also is high enough, then a dust explosion can occur. This is also an auto ignition phenomena. Now, let us take another example of compartment fire. Take a small room and there is a fire due to burning of some commodity or some say for example some material like chair, etc. in the room. Now, this room is not having much ventilation. Under this condition, what happens is, first of all, the heat which is released from one commodity can be used to heat up the neighboring commodities, which is going to cause, at a particular time, it will cause a flashover. Flashover is the phenomena where simultaneous ignition occurs due to the heat released from one of the commodities in the room. Okay, for example, if the smoke which is formed due to a fire reaches a temperature of say 600 degrees centigrade, then that temperature is enough to cause ignition of the other commodities in the room. So, there are some observations like that. Now, one more situation is, if there is no much oxygen present in the room and some particular material is burning in the room. But due to non-availability of oxygen, after a partial burning, the burning will cease because oxygen is cut off. In the fire triangle, if fuel, oxygen or heat is cut off, the fire will cease. In this case, due to limited availability of oxygen, the fire will put off. So what happens? Now fuel vapors will be there, which will be hotter also because fire has occurred, so it has heated up the material. So fuel vapors are present in the room which are hot enough. Now suddenly if some gust of oxygen comes in, say for example some windows is open or some door is open, then what happens is the oxygen will be able to mix with the fuel which is hot enough so that immediately it will burn. So such a phenomena is called backdraft. So where the hot fuel gases will be suddenly exposed to a stream of oxygen or air. So these are all several phenomena. These are related to auto ignition basically. Definitions like spontaneous ignition of dust layer, then dust explosion, then compartment fire scenario you will have flash over, then you have again in the compartment fire scenario a backdraft. So these are all terminologies related to auto ignition. Now let us go to next definition, which is for flame heat flux. Okay, now let us say ignition occurs over a material. So for example, this table is ignited somehow. So due to some accidental ignition source, it is ignited. The flame is established over the material, and first of all, for the flame to burn in a sustained manner over the material, we need to have a proper flame heat flux. That means some heat has to be transferred from the flame back to the surface in order to produce more vapors or the gases and sustain this flame. So once the flame is initiated over a condensed fuel surface, a parameter called flame heat flux dictates the sustained burning. Okay, flame heat flux is the, see for example there is a fire, some amount of heat from the fire or the flames will go to the surroundings, some amount will be given back to the surface, that is a fraction of the heat will be given back to the surface, that is called flame heat flux. Now we know already, we have seen that when a particular material, say 1 kg of a material completely burns, you get the heat of combustion. Now part of this heat is carried away by the product gases. For example, the gases, a smoke, which is hot gases with some carbon particles, is called smoke, that leaves the space. So part of the heat is transferred due to the movement of the product gases away from the fire scenario, and this contributes to what is called convective heat flux. Next is, some amount of this heat is radiated away to the atmosphere, that is radiative heat flux. Okay, now fuel surface will receive a part of the heat flux. This heat transfer can be due to conduction, convection as well as radiation. Okay, so depending upon what surface. For example, in solids, the radiative heat transfer feedback to the surface will be considerable. For liquids, it may not be so high, and so on, based upon the surface area and the material properties. So the rate or the ratio of the heat released to in the fire, that is the heat of combustion, and the heat required to pyrolyze the unit mass of material. For example, in the condensed fuel, solid fuel, how much heat is required to release the volatiles, or in the case of liquid fuel, how much latent heat has to be supplied. Okay, this ratio is called heat release parameter. Okay, so that means we have to understand the material first. Okay, what is the amount of heat required for it to pyrolyze, and what is the amount of heat which will be released when it burns. So the flame or fire can be characterized only when the material is properly characterized. So now I have shown a scenario here where you can see that when there is a fire, this is a small pan. say 50 centimeter pan where there is some fuel, liquid fuel, and we have ignited the liquid fuel so that a fire forms. This is a turbulent fire. You can see that very lot of oscillations are there. It's a turbulent fire. Now, part of this, so for this fire to sustain, it's a non-premix fire, so that the fuel vapors come out from the surface of the pool, air from the ambient comes in, and now you can see that part of the heat from the fire is given back to the surface. Okay, this is basically, you can say, radiation dominant this. Now, some of the heat is given to the ambient. Again, say radiation will not dominate, because see, radiation will dominate in fires which have higher luminosity, soot, etc. The radiation heat transfer will dominate. Obviously, there is a convective heat loss where the heat is carried away by the products, the dark smoke, etc. It carries away the product. So, that is also there. So, now if you see, let us focus on the radiation heat transfer. You can see that the radiation intensity or radiative intensity versus wavelength. You can see that this wavelength has a regime. For example, low wavelengths is contributed by ultraviolet and visible, a small amount of visible radiation. Plus the species, say for example H2 and CO2, etc., will contribute to some amount of, some region of wavelength, and its intensity is quite high basically. When CO is formed, CO2 also will contribute to some amount of radiation. So, this radiation heat transfer basically depends upon the wavelength of the species, and the intensity is calculated based upon that. You understand? So, this is very important to understand. So, the heat transfer to the surface will be a small fraction. Other than that, the heat released will be spent away by radiation to the ambient plus convection to the convection through the transport of the hot gases. Now, the next set of definitions will be for flame spread. Flame spread means what? So, if I try to take a table or something, in which in a particular corner I try to ignite, a particular edge or boundary or corner I try to ignite. Okay, this is done as a part of test. See, for example, when you want to use a material for any domestic purpose, we have to understand whether it will cause fire hazard or not. So, that means, if so, for example, if ignition temperature is less, heat of pyrolysis also is less, etc., then that particular material will easily catch fire. Okay. On the other hand, if the ignition temperature is high, heat of pyrolysis is high, etc., then it will have some fire resistance. For example, if there is an environment where you have some heat flux which is possibly can come in. So, say some industry where there is a hot space and through which some heat flux can come in. So, there you have to use materials of very high ignition temperature, very high heat of pyrolysis. That means the material should not be affected by the heat flux which is coming in. So, once the material is ignited, the flame actually spreads over the material in a time dependent or transient manner. Okay, a flame forms on a material at a given location, and this flame spreads over the material, but this flame spread again depends upon several factors. Basically, when you do experiments in some devices as per some standards, you will get what is called flame propagation index. The flame propagation index FPI is determined usually using the set of standard experiments, and that will tell you the hazardous nature of the material. For example, how fast the flame can spread over the material. Higher the value of FPI, higher will be the flame spread rate. What is flame spread rate? Basically is the sequence of ignition. See, I ignite in a corner of a table. So, for example, table is like this. I ignite at a corner of a table, and the flame spreads like this. So, that means subsequently it ignites the next layer, and again ignites the next layer and it passes on. So this is this flame spread. The rate at which it actually goes spreading over the material is this flame spread rate. Okay, so the factors that affect the ignition will also affect the flame spread rate. Now we have to define for solid materials in particular something called thermally thin or thermally thick. What is that? See, for example, if you take a thin paper, for example, and try to ignite it, you can ignite it very easily first. Then the flame spreads over this paper very fast, consuming the paper. Why? Because whatever, see, the thickness is less, so that when you try to ignite it, there is no heat loss to the depth of the, because thickness itself is very less. So whatever heat flux comes in uniformly heats the entire thickness of the material, so that the ignition is accomplished faster. Similarly, the subsequent ignition is also accomplished faster at a faster rate, so that the flame spreads over this material much faster. So something in which the in-depth conduction or in-depth heat transfer is not very important, such materials are called thermally thin. On the other hand, you take a thicker slab of some material. Now heat flux comes through one of the surfaces. There is a different thickness. So what happens? The heat flux which is coming in will be, first some radiation will occur. So for example, take a material which is thicker like this. Some heat flux comes in. Okay, heat flux comes in, say Q in, I will say Qi. Now some of the heat can go out from the surface itself, say I will say QR, so due to radiation. Some can be conducted inside, QC, within the material. Now if these heat transfers, this heat transfer within the material is significant in nature, that is, we cannot neglect this QC which is coming inside due to conduction into the material, then such materials are classified as thermally thick materials. You understand? So that means if you take a thinner material, the heat flux comes in, some heat can go out, but that is inside, within the material, the heat which is conducted will be not needed. That analysis is not needed. So that means that the temperature gradient within the material, within the solid, will be almost equal to 0. So if the temperature gradient within the solid is close to 0, then it is called thermally thin. Please understand, geometrically it may be thin or thicker, that is different. Thermally thin means how much is the thermal conductivity of the material and how fast heat can be transferred inside this, or how fast the temperature becomes uniform within the material. That is what is going to dictate the categorization of thermally thick or thermally thin. Now, this is one of the things. Then coming to the next flame spread, I ignite at particular point and the flame spread over the material. So now there will be some airflow, okay, or there will be some forced airflow, say some fan may be running, so forced airflow may be there, or there can be some natural convection airflow. So if the flame spreads in the same direction of the airflow, then it is called concurrent flame spread. In the case where the flame spreads opposite direction to the airflow, then it is called opposed, as the name suggests, opposed airflow. So let us see some examples. So let us consider, for example, natural convection scenario. Let us consider this flame spread in a vertical material. Now in the vertical material, I try to ignite at the bottom somewhere here. A flame forms, and now the flame is going to go in this direction, upward direction, consuming, because I am in the vertical plate, I am igniting at the bottom. So the flame has to spread over the material, moving towards the top direction, upward direction. Okay, now what is the airflow direction for this? Natural convection. So as a flame, the air entrains from this surface and it goes. It also, the hot gases rises up. So then the airflow also will be vented to this, entrainment will occur like this. So since the gravity creates a buoyancy force, and buoyancy force is due to the density gradient. The airflow direction will be against the gravity direction. So, the gravity vector is upside down. So, the airflow, induced airflow around the flame, correct, because away from the flame there will be no flow. Around the flame, the induced airflow will be in the upward direction. When the flame also spreads in the upward direction, then it is called concurrent flame spread or upward flame spread. On the other hand, if you have the same material, but now you ignite in the top portion, here you ignite. Now the flame has to propagate in the downward direction, but the buoyancy induced airflow is in the upward direction against the gravity vector, correct? So what happens? Now the flame has to spread in the opposite direction of the induced airflow. So this is called downward flame spread or opposed flame spread. The natural convective environment, because there is no force flow here, the natural air entrainment occurs, which actually occurs and goes against the gravity direction. So where you ignite, the airflow induced is upward direction. When the flame also spreads in the upward direction, it is concurrent. The flame propagates in the downward direction, it is opposed. So now coming to the force flow, when the airflow is from say left to right, there is a horizontal surface. I now ignite at the left edge. Then the flame has to again spread from left to right, which is exactly the same direction as the airflow. Now that is called concurrent flame spread in a force flow. On the other hand, if the airflow is from left to right as in the say the previous case, but now I ignite the right edge here. So previously I ignited the left edge, flame also spread from left to right. Now I ignite the right edge, so that the flame actually will spread from right to left. Now what happens? It opposes the airflow direction. The flame spread opposes the airflow. This is called opposed flame spread. What happens is, in the opposed flame spread, either here or here, the flame spread rate will be very, very low, gradual, and it will be steady, almost steady, because this flame will heat up a smaller portion only below that or left side to this here, and it will ignite and slowly propagate in a steady manner. On the other hand, if you take the concurrent or the same direction flame spread, you can see that the heat flux, the flame actually tilts over the surface and it may heat a larger portion, and due to heating of larger portion, the flame will rapidly spread. Okay, so even here in this, it will heat a larger portion, but in the case of opposed, it will only heat a small portion next to it. As it spreads, it will only heat a smaller portion and gradually spreads. So concurrent flame spread is rapid and it is unsteady, because as the flame propagates or spreads, it will heat some area in an unsteady manner. But on the other hand, as I told you, the opposed flame spread will be gradual, slow, much slow and steady, almost steady. Now, next we go to the definition related to mass burning rate. Okay, so let us take a scenario. Slowly flame has initiated at a particular corner or edge or boundary, then it has spread over the entire material. So for example, you take horizontal thing, you ignite here, the flame spreads over this, and there is a flame fire which is formed over the entire surface. So this is what is shown here. Now once the flame occupies the entire surface, now there will be a coupling between heat and mass transfer. Even when it spread, there will be a coupling, but here this coupling will be almost steady. So there will be some amount of heat which is given, some amount of heat which will be lost, some amount of heat which will be used to produce the fuel gas. So the fuel gas again feeds the flame. So this cycle repeats. So what happens? This is a horizontal. In vertical configuration also, when the flame spreads over the entire surface, there will be a almost steady heat and mass transfer processes. So once the flame spreads over, because again it depends on thickness also. If you have a paper, as the flame spreads itself, the paper will be burnt, it will be consumed. There is no steady process, it is only transient process. But if you take a thick cardboard and ignite it, first the flame spread will be faster. It will first spread over the entire surface and then consume the cardboard. The consumption of the cardboard after the flame spreads over the thicker cardboard plate will be almost steady. So, we can say that depending upon the thickness, convection, etc., the burning rate will be determined. Once you have thicker condensed fuel surface, thicker condensed fuel, then you will see that you will have steady burning for some time. Okay. Even though it is unsteady, the rate at which the burning takes place will be steady. Okay. So, once the flame spreads over the entire surface of the material, several factors will dictate the burning rate of this. So, the flame actually sits over the material and consumes the material almost at a steady rate. Again, if thickness is very small, fuel content is very small, then it will be transient. If there is see, for example, why we are saying thickness is a factor here? Because thickness will correspond to volume. The volume of the material, density of a condensed fuel is very high. So, for liquid will be 900 kilogram per meter cube. Similarly, solid also you can see it is a very high dense thing. So, that is what we called it condensed fuels. So, the condensed fuel, the mass coming out is at a smaller rate. So, slowly the mass will come out. See, for example, if you take gas, density is say 1 kilogram per meter cube, then if you have some fixed volume, okay, say 1 meter cube, then only 1 kg will come out. But in the 1 meter cube volume, if you have a condensed fuel, then you will see 900 kgs of mass is there in that. So, that has to come out. So, you see that basically be dependent on the thickness or the depth of the fuel, you will see that the mass will come out slowly and a steady burning will be established. So, that rate is called mass burning rate. The steady burning of a material under given circumstances, because this is also dependent on several circumstances like for example, fuel thickness, then gas phase convection and the heat loss. If you lose more and more heat, the mass burning rate will be lesser and lesser. So, heat loss means, for example, if you try to extract the heat out and there is no or limited heat feedback occurs to the surface, then the mass burning rate reduces. Of course, material properties also is going to dictate this. Okay.